Hello everyone. Today I'll be explaining this Python notebook designed for a regression task using the PyCaret. This notebook demonstrates as an end-to-end machine learning pipeline from data preprocessing to model evaluation and prediction. And I'll explain the decisions made at each step and evaluate the model's performance and reflect on the strategies for improvement. So let's begin. For this data set, this data set contains medical insurance data, and the goal is to predict the charges based on features like age, BMI, and other demographic details. And the feature selections were made using the recursive feature elimination, the RFE, that is to identify the most important predictors. This reduced the dimensionality and enhanced the model interpretability by excluding the irrelevant or redundant features. The selected features were then combined into DF selected along with the target variable charges. This ensures we focus only on the impactful predictors and improving the model's efficiency and accuracy. Selecting features proactively also helps prevent overfitting by reducing noise in the data. And for the PyCaret setup, we use the PyCaret to automate preprocessing and modeling. And in this setup step, the following configurations were made. We first set the charges as our target variable, and then we did the normalization, that is to ensure all features are on the same scale, which is critical for models sensitive to feature magnitude. And we also did the multi-collinearity removal, that is to enable to that is to automatically drop the highly correlated features, improving the model stability. And we disable the feature selection here because in the RFE step, we have already done that. This setup phase standardized the data and ensures the consistency across the models, making it easier to identify the best performing one. For the model comparison, using the PyCaret's compare model function, multiple regression models were compared, and initially models were ranked based on the R-square to evaluate their ability to explain the variance in the target variable. From this, we select the top 5 models for further analysis. To refine the selection, these models were evaluated using the mean square error, the MSE, which prioritized the models that minimize the prediction errors, aligning with our goal for accuracy in predicting the insurance costs. Interpreting the learning curves and model evaluation. To diagnose the model fit, we use the learning curves and error analysis. There are 3 possible outcomes. First is the underfitting, that is models with high training and validation errors across all data points. And this indicates the data is too simple to capture the underlying patterns in the data. The second one is the overfitting, the models, that is models with low training errors, but significantly higher validation errors. This suggests that the model memorized the training data set and failed to generalize. The third one is a well-fitted model, that is which show the low training and validation errors with minimal gaps between them. A well-fitted model balances the bias and variance, making it ideal for real-world predictions. And using these insets for the overfitting models, we adjust the regularization parameters and simplify the model complexity. And for underfitting models, we recommend increasing the training data or using example methods to capture more complex patterns. These adjustments were guided by observations from the learning curves and error distributions. That is to ensuring the models were both accurate and generalizable. And for predictions and submission, for predictions, with the predict model function was used on the test data set, the DF test RFE, and here's our process. Predictions were generated for each of the top models, and a submission file was created for each model, dynamically named using the model's class name. And this systematic approach ensured organized outputs and allowed easy tracking of all predictions. And each submission file contained 2 columns. The first one is the ID, that is a unique identifier for each test instance. The second one is the target, that is the prediction value for the insurance charges. And for some and to move forward, after analyzing the learning curves and the model performance, it is clear that the best performing model is well fitted. However, there's still always room for improvement. And here are some innovative suggestions. First is ensemble learning, that is to combine predictions from the top 3 models, which could further enhance the accuracy and reduce the variance. The second one is about the hyperparameter optimization. Advanced tuning models such as Bayesian optimization could identify better configurations for the models. The third one is the feature engineering, that is like creating interaction terms or transforming features could improve the predictive power. The last one is the cross-validation strategies, that is to use the stratified k-fold cross-validation, which would ensure robust model evaluation, particularly for imbalanced data sets. By implementing those strategies, we could potentially achieve even higher accuracy and generalization. And that's so much for today's presentation, and thanks for your close attention.